It is shown in Appendix 4.3 that the total sum of squares equals the explained sum of squares plus the sum of squared residuals. That is, TSS equals ESS plus SSR. Thus, the R squared can also be expressed as 1 minus the ratio of the sum of squared residuals to the total sum of squares. Big R squared equals 1 minus the sum, the total sum, 1 minus the SSR, which is sum of squared residuals, over the total sum of squares, TSS. Equation 4.16. Finally, the big R squared of the regression of big Y on the single regression X is the square of the correlation coefficient between big Y and X. Exercise 4.12. The big R squared ranges between 0 and 1. If beta sub 1 hat equals 0, then big X sub I explains none of the variation of the big Y sub I, and the predicted value of big Y sub I is big Y sub I hat equals beta sub naught hat equals big Y bar from equation 4.6. In this case, the explained sum of squares is 0, and the sum of squared residuals equals the total sum of squares. Thus, the big R squared is 0. In contrast, if big X sub I explains all of the variation of big Y sub I, then big Y sub I equals big Y sub I hat for all I, and every residual is 0. That is U sub I hat equals 0, so that the ESS, the explained sum of squares, equals the TSS, which is the total sum of squares. And big R squared is equal to 1. In general, the R squared does not take on the extreme value of 0 or 1, but falls somewhere in between. And big R squared near 1 indicates that the regressor is good at predicting big Y sub I, while and big R squared near 0 indicates that the regressor is not very good at predicting big Y sub I.